Hello, everyone, and hello again if you attended the earlier presentation. If you did, I apologize because there's going to be some overlap, of course, with the previous presentation. But just to set up the stage, what are we trying to do with graphical neural network in liquid argon TPCs? So this is an example of an image that we get out of a 3D reconstruction RTPC. So this RTPC in particular is just a simulation of the dune detector, which is not in operation yet, but will exist in the near future. And this detector is roughly 100 cubic meter of liquid argon. And we can get in this detector up to 20 neutrino interactions. And of course, what this can create is a pileup between different neutrino interactions. So we want to try to put the different particles and showers together into interactions. So trying to do interaction grouping. And before we can actually get to that step of interaction grouping, we need to look within interaction and try to do a shower grouping. So we need to have shower objects before we can try to assemble them into an interaction. And so here I'm giving you an example of a neutrino interaction on the right-hand side, where you've got 3 different showers coming out of the interaction vertex. And so we want to try to cluster these 3 different showers into 3 separate objects. And so this is the task that I'm going to present first and then explain how we adapt this task to the interaction clustering. Just going through roughly the architecture that we use to do this, we start with a shower voxels that we reconstruct in the detector. And this is actually given by the upstream reconstruction chain. So if you want the details about the full reconstruction chain, please listen to the recording of my previous CTD talk. And what we do is that we first fragment the shower voxels into shower fragments. And there are different ways to do this. One is to use a CNN that I presented in the other talk, or is simply to run dbScan on shower voxels. This actually works quite well. And then when we have fragments, then we can start to try to extract information about these fragment features so that we encode these different fragments into nodes into a graph. And then we make connection between these different nodes in the graph, and we try to infer information about these edges and these nodes. And the way that this is done using a GNN, as you've heard a couple of times today, is by doing message passing. So essentially at each step of the message passing, we update the node features by taking in the edge features that are connected to that node, but also the nodes that are connected to this node through the edges. And we also update the edge features by taking in the features coming from the nodes that the edge connects together. And we can repeat this process of updating the node features and edge features. And then at the output, we use these edge features and we reduce them to an edge score essentially. And we try to predict which edges are on and which edges are off. So which 2 fragments in a shower are connected and which are not. And we also want, once that we have the prediction about the group, to try to predict which node within each group is most likely to be the initiator of the shower. So this is primary prediction. So just to get a little bit, to give you a little bit more detail about what we're actually looking at. So this is the output of a previous reconstruction chain. We've got different shower fragments in our detector. And what we do first is to extract features, simple features about each of these fragments. And one way to do this is just to extract geometrical features. So we take the centroid of the different fragments. We take the principal component vector, which is essentially the orientation of these ellipses that are represented on the right picture. And we take the covariance matrix, which represents the spread of these different fragments in space. And then we build an input graph. And the way that we build an input graph actually is just to connect every fragment with every other fragment. So that's a complete graph. So we allow every fragment in the image to communicate with every other fragment. And we also input some edge features. So we give information about the displacement between fragments. So essentially the vector that connects the 2 points of closest approach to the 2 points of closest approach of the 2 fragments that it's connecting. So on the right-hand side, I've just represented the edges with a color scale that corresponds to the distance between fragments. Then what we do is that we do message passing. So we start with node and edge features that I just described, and then we want to update these node features and edge features. There are many ways to do this, and the ways that we have gone with, because we've optimized and showed that this was the best way to do it, is to use this NN-conv layer for node update and to use this meta layer for edge update. So I invite you to check out these papers for more detail. And we do this edge and node updating 3 times. The reason for this is that if we do the update more than 3 times, it turns out that it doesn't improve the predictive power of our reconstruction. And what we're actually trying to predict that's important is that we want the network to say that an edge is on if it connects two fragments that are within the same group. So we are kind of building a complete graph within each of the shower groups. This is our target. And so let's say that the network gives us prediction like the one on the right-hand side. So this is what we are trying to predict on the left, and this is what the network gives us on the right. What you can see in this example is that it makes a couple of mistakes. So it's, for instance, connecting the top fragment with the right shower here. So it's connecting this fragment with this shower, even though they are two separate objects. And so if we just threshold the edges and say, okay, if an edge has a score above 0.5, we just turn it on and we put them in the same group, you can see that this will be a mistake. But what you can also realize is that this fragment is only connected to one of the fragments in this group. So it's a pretty weak connection. And so there is a better way to interpret the edge cores coming out of the network. So here I'm just giving you an example of a simple image where you would have 8 different nodes, right? And I also give you the edge core prediction from the network. And what you can see is that the network disconnected all the edges, all the nodes correctly, apart from one pair of nodes here, where it has some confidence that these two nodes are connected. And so if you simply threshold, then you make the wrong group prediction. And you can see that if you calculate your cross entropy loss, so you compare the edge core with the edge that you've predicted. So essentially, if you put 1 and 5 in the same group, then you are also putting 3 and 7 in the same group, which means that suddenly your score for your graph is bad because you've put two nodes that do not belong to the same group and they have a low score together into the same group. So what you really want is to find a partition of the graph that minimizes this cross entropy loss when you compare the predicted adjacency matrix and the true adjacency matrix. The problem with this is that, of course, there is a lot of different possibility of partitioning a set. If you only have 20 fragments in the image, which is actually pretty low, you already have 10 to the 13 possible partition of the set. So you cannot brute force attempt to produce every possible partition and connect every possible node together. And so the way that we do it instead is that we start with an empty graph. So we have every fragment being their own group, and we compute the cross entropy loss for this. So here the cross entropy loss will be bad, for instance, because 1 and 2 should be connected. They have a high edge core, and here they are disconnected in this grouping, in this partition. And so we add the edge sequentially by starting with the most likely edge, and here we've added the most likely edge that connects node 1 and 2, and you can see the score goes down. And we repeat this process until we reach a point where we have no edge that are proposed with a score above 0.5. And what you can see here is that the optimal graph that we get is this graph, where we don't have a connection between 1 and 5, because if we made that connection, then our cross entropy loss would increase. And so on the right-hand side now of this image, you can see that we've recovered the correct grouping, even though we had some mistakes in the edge prediction. And on the left-hand side, I'm giving you some metrics of the quality of the shower clustering task. I'm giving you purity, efficiency, and adjust-in-rand index. Purity is basically a measure of over-clustering. So if you're over-clustering, your score goes down. And if you have a perfect partition, it goes to 1. Low efficiency is a measure of under-clustering. And error is a measurement that's quite stringent on the similarity between two partitions. For the node prediction task, which is trying to predict the initiator of a shower, this is actually quite useful for us because it gives us essentially the start point and the direction of a shower, which is useful for instance, in pi-0 reconstruction. And here on the left-hand side, I'm showing you this primary score for primary nodes, for true primary nodes in the orange. So you can see the score is close to 1. And for secondary nodes in the blue. So you can see the score is close to 0. Typically, if you take all the predicted groups and you look at the most likely primary nodes, the network gets it right at 98.5% of the time. And then the extension of this task is to use the same algorithm, but instead of trying to cluster shower fragments together into shower instances, we try to cluster particle instances into interactions. So on the left-hand side, what you can see is an example where you get two neutrino like interaction in an event overlaid with some cosmic rays. And they are both colored in a different color because they belong to different interactions. So you've got a green one here and you've got a blue one on the right-hand side. And you want the network to be able to reconstruct this grouping. And we use essentially the same architecture to do this. On the right, at the prediction, you can see that it did a pretty good job at clustering these two neutrino interactions. In this particular example, it made a mistake of clustering this small energy deposition here together with this neutrino interaction. And so if you look at the efficiency, purity, and error, you get comparable numbers to what you had for the shower clustering test. So the reason why I'm highlighting 2 here is because this is the expected neutrino density that we get for an image of this size. So I'd just like to conclude that these are 2 crucial reconstruction steps in the liquid argon TPC, and that these have been resolved by using these graphical neural networks. So there's one that's shower clustering, and the second one is interaction clustering. And also, I didn't talk about particle flow specifically, but you can see there is a clear path to particle flow from what I described. So currently, we are letting the network figure out which edges it likes to turn on for itself. But of course, we could also enforce that the network predicts physical edges. So if there's an actual photon connecting 2 fragments of a shower, we want the network to turn these edges on specifically. And if you want more information about the full chain that I've just schematically represented at the top of this image, please check out my other talk. Thank you.
Great, thank you. Other questions? David.
Yeah, interesting talk. So I'm still trying to understand in your example how the shower fragment that's shown on, I think it's, I'm trying to scroll to the right line, but
this one's slide 6?
Well, I understand that so your adjacency measure is allowing you to eliminate this connection between the original incoming particle and the secondary shower, but there are similar topologies in other parts of your graph, and I'm not seeing how they have distinct adjacency. For instance, this one on the lower bottom there, it looks like it's another case where you've got one node connected to one node. Why is that not also a low adjacency?
Oh, this one?
Yes, for instance.
But so yeah, this one is disconnected from these 2 actually. When you look at the prediction, you can see here.
But you still got the vertex between them, the edge.
So you're saying we keep this one?
Yeah, I'm asking how you can keep that and not and eliminate the one that you were trying to get rid of, which is the one on the top on the right.
So it just picks whichever is most likely. So basically here you've got maybe 2 or 3 fragments, and they're only connected to one of the fragments in this shower, right? So if you make a connection between these 2, you're gonna have a lot of mistakes, so your loss gonna go up. But here connecting this one with this one works because there's it's connected to every fragment in this shower. So there's one large fragment probably and one other subsequent fragment, and it's connecting to both. So it makes sense to put them together in the same group.
Huh.
Does that make sense?
Well, not from the visual information on this slide, but maybe there's more going on than what I can see.
I didn't cheat, I swear.
Okay, something to think about and come back to in the Q&A session. Any other questions? Oh, okay, thank you again, Francois.
Thank you very much.